Hello and good evening. Welcome to this evening's webinar. We've got an excellent webinar lined up for you this evening, coming to you from Queensland, live from Queensland, developing concepts in Year 10 mathematics, which builds beautifully on one that we ran 2 weeks ago, which was investigations in Year 10 mathematics. My name is Brian Lannon. I will be your host for this webinar, and you hear my dulcet tones coming to you from Yakandanda, Victoria. But you don't want to listen to me all the time. You'll be much better off listening to your presenters, Shelley Cross, who is at St Hilda's School at the Gold Coast. And Shelley, like myself, has been teaching for a few decades now, and the last 5 of which being at St Hilda's School. And prior to that, she was a teacher mentor. You can read these things on your screen. Our other panellist this evening is Jim Lowe. Are you with us there, Jim?
I certainly am, Brian. Good evening, everyone.
Fantastic. And Jim comes to us from Queensland University of Technology and has been involved in a whole lot of things, one of which I know is helping organise the Queensland State Conference, which is coming up fairly soon. So you've heard enough from me. I'm going to swap you across now to Shelley, our first presenter. So thanks, Shelley. Now, Shelley, these files that you've been making, what software have you used for that?
I've used the TI-nspire app software for the calculator videos that you'll see tonight. With some of the videos I've made for the iTunes course, I've done a screen capture of the iPad interface actually, and I've done most of that on iMovie.
Aha. So it's all Apple based, I'm seeing.
Yep.
Terrific. Well,
yeah, at our school we're using the TI-nspire CAS app at the moment. We'll go over to the non-CAS calculator next year, but the girls have iPads already, so it made sense to just use the app. Right, so the place that we're going to start with today is looking at developing geometry pictures which can help students understand some of the circle geometry theorems. So I thought I'd start by just running us through how to actually develop these pictures using the geometry tools.
I might run a little quiz in the background while you do that, Shelley. Watch for the live polling. I have a question ready for you.
Oh, great. Okay. So I think shall I just start with the...
Yep, no, you keep telling us, showing us your things. I've just got a couple of questions to ask the participants.
Okay. Right. So we'll start by adding a geometry page. There we go. It's a little bit slow, I think. It can come through, yeah.
Delay there. I'm seeing your calculator and I'm seeing the screen opened at, add geometry.
There we go, add geometry. So in order to add the circle, we start with using the menu tools. So we're going to go menu, and I'll just watch my other computer to see how the lag goes. Menu, shapes.
Yep.
And then across from shapes, we're going to go to circle. To put a circle into the screen, you click once to put the center of the circle, move away from the circle, the center, click again, and now we have a circle. There is a point on the circle, so we generally need to just push escape to make that circle stay on the screen. To put a point on the circle, so what we want to do is we want to put 3 points on the circumference of the circle, join them with line segments, and then measure the angle that's made across the arc. So we'll go back to menu, points and lines, and point on. Now this is really easy to do on the calculator, just as easy as on the software. So we click once on the circle, it puts a point on the circle, click twice to make the point stay. Click once on the circumference again, click twice to make the point stay. Actually I might put 4 points on the circle. Click again, click twice, and click again, click twice. You'll see that my pointer still is on a bit of a point thing, so up here you'll see the point icon, so we push escape to get rid of that. Now I'm going to join these points with some line segments. So back to menu, points and lines again, and segment. To do the line segment, we click on a point and click on the next point, and there we have my line segment. You'll notice as I move away, I'm still on the pointer, so I can actually join a couple more points together. So I'll click on the same point I was at, and back down here, and maybe we'll go to the center of the circle as well. So we'll go from the arc to the center, from the center, back to the circumference. And push escape to get rid of that tool. To calculate the angle now, so with the circle geometry, we really want the kids to see the angle opposite the same arc. The angle at the center of the circle is double the angle on the circumference. So we need to measure those angles. We'll go back to menu, measurement, and angle. Click on the 3 points that make the angle, and there we have the angle. On the inside, we click on the 3 points that make the angle, escape, and here we have our values. The nice thing about this is if you click and hold to drag that point, you can actually move that point live in front of the kids and show them that that angle actually doesn't change no matter where on the circumference it is, provided it's opposite the same arc. What will change this angle on the circumference is if we change the size of the arc that it subtends. So I think that's really the first thing that I wanted to show you, was how to actually make these diagrams. It's really very easy in the geometry page. It's got tools to add in the points and lines. We can put a tangent at any point on the circumference just by clicking on the circumference, again escape, and we can make that tangent as long as we like. Because I've clicked on the point that was on the circumference, that tangent is pretty much stuck on that point, no matter where I move it around the circle. It's also useful to be able to label the points. So again, menu, actions this time, down to text. And if I actually click while that point is selected and call that point A, escape, point A, click somewhere else, that label is actually attached now to that point. So I can label the line as a tangent. I can label this point here as point B. So you'll notice that the text tool is indicated as selected. To drop the text, the selection, I just push escape on the calculator screen. Okay, now I can actually move these labels around if I need to make my diagram look better. And those labels are now attached to the things that I put them up against. Right. Any questions about all that?
I'm just looking, somebody said please show one more. I don't know if that means one more time or one more example. I think people are liking what they're seeing.
Right. What could I do?
I don't know. I was just writing to ask
Okay.
one more what. So if that participant wants to elaborate. Meanwhile, I've opened a poll on 2 questions, which about half of our participants have answered. First question being, did you attend our earlier webinar titled Investigations in Year 10 Mathematics, which was 2 weeks ago on the 10th of May? Your options are yes, no, or I watched the recording and I downloaded the associated files. Aha, which is quite smart as well. And the second one was, have you used these geometry tools before? Your options being yes, no, or just a bit. There's an even mix between the yes and no's there, Shelley. So
Okay.
some people, yeah. So some people will have got some great benefit from what you've just shown us there already.
Well, maybe I'll do one more diagram if people want to work alongside with their calculators. What do you think, Brian?
I reckon that would be a great idea. Calculators at the ready.
Okay, so we'll open a new geometry page, home, and this is the geometry page here. And again, we'll start out by putting a circle in the center of the screen. So to do that, I'll go a bit slower. We've got menu, points and lines. Oh, no, well, not points and lines, sorry, shapes. Menu, shapes, and the shape we want is a circle. Put that circle on the screen, click once, anywhere, move away from what is now the center to another location, and click once. Plus, and escape. Right, so I'm going to get rid of that. Right, what we're going to do this time is we're going to put the diameter of the circle on the screen. So in order to put the diameter, we need to draw a line that goes from the circumference through the center to the other side of the circle. We need the point to actually be stuck to the center, so we're going to actually do a line, not a line segment, because we want to be able to extend that line. You'll see what I mean in a moment. So we're going to go to menu, points and lines, and we'll start by putting a point on the circumference. Doesn't matter where you put it. So go somewhere to the circumference of the circle, click once, click twice, and escape. So basically, when you click once, it's saying, is this where you want the point? When you click twice, it's saying, okay, I'll put the point here. And when you escape, you're dropping the tool. So you're not going to land up with points all over the shape. Now we want to put a line through the center from this point. Actually, let's label this point first so we know which point we're talking about. So to label that point, go to menu. We're now going to actions. From actions, go down to text. And once you've selected text, come over to the point on the circumference. Click once. We'll type an A to call that point A. And let's label the center of the circle as O while we're here. So we'll click on that point and call that O. Click anywhere else in the circle to let the point go. And to get rid of the tool, escape. So now we're going to draw a line from A through O. So we're going to go back to menu, points and lines, and this time we're going to choose line, not segment. So it's a bit of a lag now, so there we go, choose line, which is number 4. Click on point A, and click on point O. Escape to get rid of your tool. So you'll see it's created a line that goes from A through O. We'd like this line to go all the way to the other side of the circle, so it's a diameter. So move over towards the line with the hand, click, and just drag across. So I'm doing all this on my touchpad on the computer. You can do it holding the touch screen in the center of the computer on the left, but I find using the touchpad is a bit easier. Once we've got the line to go past the center of the circle, we now need to put a point on that intersection there between the diameter and the circumference. So we'll go back to menu. We want points and lines, and down to intersection points. The way we do the intersection points is click on the circle once, click on the line once, and it puts the intersection point on. So we've drawn a diameter across the center of the circle. That's quite nice because if you click and hold this point down, oh wait, maybe it's this one here, yep, we can hold point A and we can actually move that diameter wherever we want it around the circle. So we could use this now to show that the angle in a semicircle is 90 degrees. Let's put another point on the circumference. So we go menu, points and lines, point on, click once, click twice, and escape. And now we'll put line segments from A to our new point, and from that new point to the other side of the diameter. So we're going to do menu, point and line, this time it's a segment, click on A, click on the new point, and click on the new point, and click on the circumference, and escape. Last thing we'll do is measure that angle. So back to menu, now we're at measurement. You'll see there's a few things we can measure. We can measure length, area, slope, and angle. We're going to choose angle, and then click A, circumference. And that should be 90 degrees. Holding this point, I can move this point anywhere I like, and the angle doesn't change, it's still 90 degrees. So that's quite a powerful demonstration for students, that the angle opposite the diameter is 90 degrees and it never changes.
It is very powerful. It's powerful and powerfully convincing. It's not a watertight mathematical proof, but by cripes, when you can drag a point and it shows everything, how far is that away from being a proof? Maybe just not the traditional.
Yeah. Sorry?
Maybe just not the traditional proof, but by Jove, it's powerful in building the understanding, which is exactly what you said you were seeking to achieve in our introductory biography there.
So would you like to run through just a brief look at the PowerPoint, Brian, just to show the TNS file in action?
Yes, I'd love to. So I'm swapping to our other Shelley for that.
Yeah.
So, okay, well, thank you very much, Shelley number one, and participants, if you'd just like to just put your applause and messages of congratulations into the chat window, we would love to see that, see the accolades come flowing in, and for your further entertainment and learning this evening, we have now swapped to Shelley 2. Shelley 2, how are you going?
Hi Brian, how are you?
Good, welcome to the webinar. Who has on another computer, which is faster and better for the video, but didn't have the Inspire software loaded. So Shelley's going to have stern words with her daughter and ask her why she hasn't got Inspire loaded on her computer, but she does have a faster movie player. What's happening here, Shelley?
Right, so I'll just go to, this is the link to the Australian curriculum that I'm showing you here. What I've done is I've made a video just using iMovie and taking a screen capture from the TI-nspire software package, which just shows us a few of these things in action. I won't spend too long talking over it. I'll just basically put it on to show you when I find the right spot. There we go. So what I've got in the TNS file is just a few little pages showing some terminology that students should know. The idea about this TNS video was just for kids to possibly work through this by themselves even. What I've done here is I've highlighted the arc in green so that it's clear that the angles are subtended by the same arc. And pretty much your little butterfly pattern. Again, moving B away is the thing that changes the size of the angle, but both angles at A and B are the same. In the second view, this is more the traditional type of view that kids often see. It's a sort of crown shape. They tend to be able to see that two of the angles are the same, but they tend to forget the third one. So again, just a little visual demonstration. All of these are, as Brian said, they're not proofs, they're just visual demonstrations, but the fact that students can actually input this diagram themselves and then measure the angles is quite a powerful thing to help them remember.
Yeah, powerfully compelling. And the fact they can do it on their normal school calculator, teachers would be aware that there's a vast range of software available that does dynamic geometry, and it's quite good. There's some good packages available, but the logistics of whether we've got sufficient download speeds and getting your computers out or taking your students to a computer room, it is just so much in a classroom, the logistical ease of, say, okay, take out your calculator and just simply do these constructions, which of course you can send to them as well. If you're using the Navigator system, you can send these constructions to them. Shelley, I'm talking over your video.
No, that's fine. I just wanted to demonstrate it. I think I've done enough talking. But what we did find this year was that we actually gave them the circles on basically on a piece of paper already done, which with points for them to join up and measure, because actually using a protractor is a challenge for some kids. And we found that doing this kind of thing in the second lesson, just demonstrating to them live so they could see you actually put the points on, was probably, I mean, the TNS file is good, but I think it's more powerful if you do it live or if they actually step themselves through and build the pictures themselves.
Yes.
But this is just the last one, so this is just a little, what do we know? Looking at congruency, we know the angles between, I won't talk about it, we all know this. So, and then once we've proved them congruent, we can actually measure those angles at the point outside C and double check that yes, in fact, they are equal. So that was, yeah, pretty much circles in the package.
Very, very smart. What do you think of that, Jim?
I think it's tremendous, Brian. Those concepts that become so crucial, especially when kids go on to senior mathematics, so often those things get referred to, and if they've only half learned them or half understood them in year 10, it just makes what should be like a simple, straightforward application question a really difficult task for them because the background knowledge is not there.
Mm. Yeah, an appreciation of how it looks. What's this on about? What's all these segments and angles and stuff? So we need the physical and the fact that it's interactive. So thank you very much there, Shelley.
Thank you, Brian. Thank you, Shelley. Where am I going there? That'll get me started.
That'll do.
So,
That looks good.
On with this concept of developing concepts in Year 10 mathematics, I'm going to take a little different tack. Shelley's given you an excellent little introduction there and how you can develop the fundamental understanding of these concepts with kids. And I'm going to look at a problem that requires them to, I hope, deepen their understanding by applying it in a slightly more difficult or perhaps more complex situation. So we're going to go and search for a thing called Simpson's Line. So there's our outline. I'm not going to spend too much time on that. Let's get straight into it. So my title there of creating a purpose is not really about creating a purpose for us here tonight. It's about creating a purpose for the students. So, you know, we've got a couple of objectives from the Australian curriculum about solving linear equations using algebraic graphical techniques, including digital technology. Well, I'm going to have a look at the digital technology tonight, and solving problems involving parallel and perpendicular lines. Now, when I talk about a purpose, I talk about trying to give kids a reason to do the mathematics that we're teaching them. And sometimes when we look at, that's a typical example I found somewhere on the web of, you know, show that the line through those 2 points is perpendicular to another two. Well, yeah, the purpose on that is to get a tick on an exam or something. It's got no real purpose for the students other than demonstrating that they can do that. If we look at and these are taken from the Queensland mathematics syllabus, standards elaborations, we've got statements like that that are a leap ahead compared to those examples. So I'm trying to find an example that will allow me to give the kids opportunities to develop the skills and the things that are described in the assessment standards. And my source for this one tonight is a thing that I've mentioned on webinars before that I discovered back in 2015 at a workshop in Fort Worth at the TQ conference, this thing called Curious and Interesting Geometry. I'm not sure if the curious means that you stick a set square up your nose or whatever that is, but that's not what we're going to look at. I found this thing in there called the Simpson Line. And I've said before talking about this that it's not the most riveting read, this book. It's pretty bland, but I think that's our job as teachers, to find ideas like this and turn it into an activity that we can engage students with. And I hope that's what I've done here and that you can try it with your kids. So the first thing we actually did this as a paper folding exercise so that we developed that understanding of what this task is. If I just go back there, you know, some kids read this sort of stuff. Take any triangle and a point on its circumcircle, draw perpendiculars from P to the side of the feet of these perpendiculars, lie in a straight line, and so on. It's lots of words. We need to pull it apart and break it up into its bits and pieces so that they understand what's going on. So very quickly, the paper folding exercise, that piece of paper is just a torn off piece, as you can probably see, from a roll of baking paper, or as it used to be called, greaseproof paper, but it's not. It doesn't have that wax feel anymore. It's just the baking paper, and it's got the advantage that it's sort of translucent, that you can see through it. So apologies for my photography. It was just rough. Didn't prop the camera on a tripod, so some of the images change sizes and so on. So we take our triangle with the vertices of the triangle on the circumference of the circle. We add our additional point P on the circumference, and what we've got to do is drop a perpendicular from P to each of the sides of the triangle. Now, it may have to be the side of the triangle extended to get the perpendicular. And with the baking paper, it's pretty easy. We can get a perpendicular if we fold the line onto itself. And there we go, trying to demonstrate that. You can see the line underneath, and you can also see the point P to make sure that you crease the fold where it's going to go through the point P. And then when we undo that, the folds are quite clearly shown in the paper, and we can see our points of intersection. So there's the three of them now. I actually drew that line in a little bit further so you could see we're looking for that point there, and that point there, which I attempted to show, and I think I made a mess of my beautiful paper folding exercise. So the line through these points here, T, S and R, is what's known as Simpson's line, and you can put a ruler through that and draw it, or you could attempt to fold it through there and show that it is in fact 3 points that are collinear. So our next thing is to go and do that with our technology, but I strongly recommend that paper folding exercise so that the kids get the idea of what they're trying to set up. Now, if I just escape out of my PowerPoint for a moment and go to my software, we should have one of these things set up. And I'm going to just quickly create that. And Shelley's given you an excellent introduction to the geometry tools, so I'm going to move fairly quickly through this construction. And I might use some slightly different tools just to show you the variety of what's available. And I'm going to get my circle that way, and as Shelley said, press escape to get rid of the tool. Now I'm going to use lines, and I'm going to get my lines through the circle to form my triangle and pick up that point again, because as we said, in order to get the perpendicular, we may need to extend one of the sides. So if I use segments, depending if I move the points, I'm not sure which one I'd have to extend. So I've done the triangle with lines extending out beyond the circle in each case. I need my point on the circle for point P, so a point on there, and then I need to draw my perpendicular. So this one's particularly easy because the construction involved is all done. It's readily available in the tools and the geometry menu. So I just need a perpendicular, and I want a perpendicular from this point to this line. I want a perpendicular from this point to this line, and I want a perpendicular from this point to this line. Turn the tool off. I want to highlight my points of intersection, so I want this line and this line, this one and this one, and this one and this one. So there's my 3 points, and all things being equal, if I now take a third line, or sorry, an additional line, a fourth one in this case, and I'm going to go through these 2 points, then as Shelley showed you before, I can grab the end of this line and take it through, and it appears to go through that point. Now, that's a very, very quick construction, and I guess it's up to you whether you get the kids to create that for themselves, but I think that's an important part of their understanding this particular problem, for them to create that for themselves, because if we prepare it earlier, then we can spend a little bit of time and actually draw in the triangle and add a little bit of colour and so on. And if you can see what I've done on this one, is that I've actually added 2 lines. I've added a line through these 2 points and another line through these 2 points, coloured this one blue and this one orange, and you see that they overlap. And once I grab the point P, then they stay that way. And as Brian said before, it's a demonstration, but it's not a proof. So let's move on, and what we can do is also create that same sort of construction, but this time in the graphing window, where we've also got the axes in there, so we can get a little bit analytical, and we can highlight the points and show the coordinates. Now I'm just going to undo that because it's going to get a bit messy for what I want to do.
It's handy to have them both, though, isn't it? Isn't it, Jim? To have the good quality ones that you've made up yourself with all the colours and shading, and then also have the students do some of their own constructions.
Yeah, and I mean, if we took a little bit more time, I could have colour-coded that as I went along, but it's...
Yeah.
We've got an hour.
You don't want to lose the kids on it,
We can highlight the line and coordinates equations, and there's the equation. And I can go to my purple line up here and coordinates and equations, and look at that. The two equations are the same. Again, it's still in the proof, and we still haven't done anything that we said in our introduction about those objectives about simultaneous equations and equations of perpendicular and parallel lines. So
we can do them both at once.
We can do this, and I started to look at how I could play with this by choosing particular points. And so I'm going to swap to, well, we were in here before and I didn't go back to the start. So just to highlight it, this is exactly the same construction, but I've done it this time with the graphs or analytic window in the background, and I've highlighted the grid because I've tried to make these points on the grid to keep the coordinates or the coordinates as simple as possible for the kids to work with, but of course our point P on the circle can't always get integer values for that. So what I've actually done in this, and by the way, Shelley, because you use the iPad all the time, I actually did this. This is my sad life. I was sitting reading that book on the train one morning and pulled out the iPad and constructed this.
With a set square up your nose.
But one of the things I found, and I hadn't altered this one, is it seems that every time I create something on the iPad and I import it into the software, I seems to default and I end up with these great big points all the time.
Yep.
I don't know if that's just me or something with my settings, or if that's something that happens to other people as well. But anyway, we're not here.
They could be changed by attributes, I expect.
Yeah, I can change them, and I have done on the next screen. But just, we can go to attributes, and we can put them down to nice fine points and so on.
Gotcha. Yep. Could I just quickly remind people there's a poll? Sorry, Jim. I'll just quickly remind people there's a poll running in the background. If you want to just click on a response to that. So we've only had a few responses so far. Sorry, Jim.
That's all right. Certainly encourage people to have a go at presenting and share your knowledge, because, I always say, it doesn't matter where I go. If I'm presenting, I learn things anyway from other people. So why not come on and share your ideas as well?
And I would certainly second that.
Thanks, Shelley.
Exactly. We have talent scouts in the crowd.
There's a couple of things I wanted to highlight here. I've lost. Where am I? Yes. Okay. Each of these points, I have used the menu. So right-click. See this pin one here? So that's already been pinned. All right. I could unpin it, but it's been pinned, which means I don't have the grabbing hand. I can't move it, right? Because I want the kids to work through this activity with these coordinates, right, and actually calculate the equation for themselves. What we don't want is somebody to grab the point and move it halfway through the exercise and so on. So they're pinned to the background for this case. So we're working one specific case here. Yet, even though I'm using actual values, I've linked each of these coordinates to variables. So Point A, I've simply linked it to XA and YA. Point B, B and YB, XP, YP, and so on, XC and YC. And you'll see my reason for that in a moment. The other thing I wanted to do with this, as I said at the start, the kids seem to think that this is a daunting task, yet basically we've got 3 points. We're asked to find the gradients and show that they actually have the same gradient no matter which 2 points we use. It's a fairly basic exercise, but we've got to go and get these coordinates first. So what I looked at doing was getting rid of the extra information and working it through systematically. This is this computational thinking business. Chunk it up into what we have to do. So first thing, I want this point R. Point P, and that's the reason why in this particular exercise I created it with one coordinate as the origin and the other one on the x-axis, and I actually, in our example, we drew the circle and put the points on it. This one we placed the points and then drew the circle through the point so that we could get that. So this one is fairly straightforward. We know that the equation of this line is just x equals whatever this x-coordinate of P is, and so point R will simply have the same x-coordinate as P, and its y-coordinate will be 0. So I'm going to take advantage of the CAS, and this might seem a bit trivial, but I'm simply saying that the x-coordinate of R is being defined as the same as the x-coordinate of P, and the y-coordinate of R is 0. Simple, straightforward, but now I've got those values in those variables that I can use. The next one, however, is a little bit more complicated. Let's go to this one, and this time we're using the side AB. We've got the point P, and we need to get the coordinates of the point S. So using the CAS, now I just need to find out if this is clear for everybody. Brian, can you move? I can move that pole. Okay. So at some stage here, if the equations get a bit messy, I might have to switch to the computer view rather than the handheld view so that you can see what's going on. But I think this is extremely helpful in helping the kids unpack this problem and work it through without getting bogged down in the algebraic manipulation. Sure, they have to do that at some stage, but to develop their problem-solving skills here with these concepts, I find this really useful. So anything that I put the little C symbol in front of is just a comment. It's not going to do anything. So I'm going to determine the coordinates of point S, and to do that, I first need to find the equation of AB. Now, you might have seen in the earlier version that I used, I tried doing a split screen, and it's just better to swap back and forth between the screens. If I need to look at the diagram, I can, and that's just jumped ahead on me, so let's go back there to where we were. So if I want the equation of AB, well, I've got the 2 points, and I really don't need to go back to this diagram to see what the values are because they're stored in the variables, and I can remember what the variables are. So y minus the y-coordinate of A equals, there's the gradient formula, yb minus ya over xb minus xa and x minus xa, and the calculator spits it out and says, there it is for me. And if I want to rearrange it in the form y equals, it's a bit trivial in this case because we can see what it is. I can solve that for y and it'll turn around and give it to me. So I thought I'd mention that for people that haven't dabbled in the CAS for this sort of thing. And so I can see that the gradient of this line is -4/11. So in my shorthand, GAB, or the gradient of the line AB, GAB, is given that value, and there it is. And what a lot of people mightn't know, variables are not just for numbers. this is extremely powerful because I can say the equation AB is defined as, and in order to, I'm not doing this live, I've done it already obviously, but when I was doing this, all I would do is up arrow until that was highlighted, press equals, it comes down there, press enter, and equation AB is now defined as that thing. So now I need the perpendicular, and so I know that the perpendicular through P, well, I'm going to use the coordinates of P. I don't need to go back and look at it because it's stored in there. So y minus yp is -1 over the gradient of AB, because I've already got the gradient of AB defined, x minus xp, press enter, and there it is. Now, we're getting a few messy numbers because, you know, that's fine. We're not actually manipulating the numbers. And again, in my shorthand, it works in my mind, folks, I hope it does for yours, the equation of the perpendicular to AB, that's it up there. So equation PAB is defined as up arrow, press enter, it goes down there, and there it is, it's stored in there. And this is the good thing for the kids. I know we need to teach them how to solve simultaneous equations, but in this example, we just want them to use it. And so for the intersection point, the calculator can solve that, and instead of worrying about, do I copy that or type that in correctly, I want to solve the equation of AB and the equation of its perpendicular in order to get the coordinates of the points of intersection. And here they are. Right? Notice I put in x, but it gives me y also. You can type in x, you can type in x comma y, you can type in y, it'll give you both, right? And so that's my point S. So the x coordinate of S is that one, copy it, store it. The y coordinate of S, copy it and store it. And so now I've got 2 points, R and S, stored in variables, so I can very quickly write down what that equation is, and there it is, right? And so that's actually my equation of Simpson's line, and if Simpson's line 1 is equal to, go up, copy that, paste it in, and I've got it defined there. Okay, so moving along and making the next part of the story a little bit quicker, all we're going to do is repeat that, this time with the line AC. And I won't go through in so much detail, but I used exactly the same features again. We defined AC, we got the gradient of AC, the gradient or the equation of the perpendicular. So I have both equations stored in there. Equation AC, equation of the perpendicular to AC, solve them to get the intersection x and y, store that xt, yt, and create the equation. And I did 2 things here. There's my equation that I just had, and there was my Simpson's equation line 1, and apart from little round-off errors based on the number of decimal places, you can see that they're the same. But I also took my first version of Simpson's line and said, give me that given this vertical line, given that x is equal to xt, this value that I had stored up here. And when I put this value into my equation for Simpson's line that I worked out with the first 2 points, I got y equals that, which was in fact the coordinates of point T. So 2 different ways that we came up with the thing there. So that's my experiment with Simpson's line and giving kids different versions of this. And yes, at some stage, we'd like to think that they could work through that. Now that's a long, tedious task to work each of those by hand, but I think using the CAS lets them see is that it's not a difficult problem, it's just a long problem. and if they were prepared to persevere and work it through, they would get the answer. Mind you, the CAS is not infallible. First go I had, I did it this one. These two equations didn't come out the same, and when I went through, at least this way, I've got every step documented. I can see the mistake, and you can guess where I made the mistake. Right back in the previous screen, at the very first statement, somehow I managed to get myself confused, and I had YA there and XB there. And so every statement had to be redone. But the benefit, to me, it was a powerful example of being able to, this, you know, it documents, people that say that CAS or just does it for them, well, using it this way, it's actually forced them to document every step of their thinking. And I think that's really powerful and useful, and I hope others think so too.
Yeah, and then, of course, as such becomes an assessment tool.
Yeah.
Because you can see the thinking. Yep.
And so you can see what I've done here is played around with looking at different variations. Well, let's take it. All that does is make it longer, not harder, because now we don't have a quick solution for the first point. And so the kids can appreciate that after they've seen the first one, that, yeah, I've just got extra steps to do. The steps are the same. It's no more difficult. If I persevere, I get it right. And I've played around trying to generalise it, and things get a bit slow when you start, because you can't just put any values in there. You've got to get the relationship for the circle as well. And so I found the best way to try and prove it in general terms is to move to a unit circle and the parametric definition, but that's getting way beyond year 10. But I think it's good for kids in year 10 to take something like that and show that their mathematics can actually show that that's the case. And a couple of other variations that comes from that curious and interesting geometry, just to finish off without going through them. Del Grande's line. And this time, instead of dropping a perpendicular, we got the same deal there, and we take a point P and we reflect it in each of the sides so that we get the, and again, we get a straight line. So there's a bit of an exercise there. But finding the coordinates of the reflection is not as simple and straightforward as what we had there. But it's still year 10, it's just a little bit longer. That we've got things about distance formulas and so forth and so on to be worked out there. And to link to one of Shelley's final things that she had in there, one that we found called Exploring the Eyeball Theorem. Now, the eyeball theorem, very quickly, points from, or lines from the centre of one circle tangential to the other circle, and looking at where we cut off bits, and the eyeball theorem that says that this red bit here is equal to this blue bit here. So that's a little exercise in itself for the kids. And what I tried to do there is show them that, well, first of all, show them that it doesn't, you know, we can manipulate it, but also show them that, okay, if we can show that this is symmetrical, then again, in terms of proof, we only need to worry about this top half there. And if we can show that PM is equal to QN, then our whole segment in there is equal to that one. And the proof in that one is, again, getting away, we're into similar triangles and ratios there and so forth. So I won't go into any more detail in that one, but if people are interested, I'll certainly make the files available for them to explore further. And I might leave it there, Brian, because I think we might have a bit of summing up to do, and I think we've just about gone over time. Is that right, or pretty much on time?
Okay. Yeah. Well, we're pretty much on there. So thank you, Jim, and I know people will be looking forward to taking a look at those files. In fact, from both presenters, from Jim and from Shelley, the consistent message was the mixing of dynamic geometry there and making connections for the students to link back to the algebra that they might otherwise find fairly dry on its own. So thank you to you both. Just a couple of things in. Terrific. No, I think it will be well appreciated across our viewing audience. One of our participants wrote in, Shelley, building on what you were saying with your recording software, your screen recording software, and I dare say different people will have their favourites, but somebody gave me a recommendation for iSpring FreeCam, and so I found this is for Windows computers. So he said iSpring FreeCam 8, so that must be version 8 of this. I googled that, and as you can see, I've got some YouTube support for that, how to use iSpring FreeCam 8. So for us Windows users, which I am, that is an option. So just in closing, a reminder that we have more webinars coming up on the program. Those of you obviously looking at Year 10 level to have attended this one, in a week's time, our next one coming up, coding in, well, this one's Victorian, but I dare say it would be more widespread than Victoria. I know it is, because coding is now across the curriculum nationwide. Year 7 to 10 curriculum, and you look at who we've got there. It's Frank Moyer and David Tynan. I think they're both on their way to becoming professors. So that will be a pretty high power webinar next week. So same time next week. Also, Year 10 teachers, as I know you will have appreciated this evening's webinar, you can look back in the webinar archive to 2 weeks earlier. You told me in the live poll that only about half of you attended this one, Investigations in Year 10 Mathematics. That was also from a couple of Queensland presenters, Melissa Hourigan and Rodney Anderson. I hosted that webinar, and I can assure you that that also was of a high standard, absolutely excellent range of ideas. So lots to follow up there. And thank you once again to both of our presenters. My name is Brian Lannon. I've been your host this evening, and I look forward to seeing you all again.
Thanks, Brian.
Farewell to all.
Thank you.